In today's video, we're going to be going over the Monte Carlo approach. And in particular, we're going to be focusing on using Monte Carlo simulations for options pricing. Later on, you're going to realize that Monte Carlo is a very general technique, and in algorithmic trading, you can in fact apply it to many more applications other than options pricing. So I prepared this PDF that'll help us understand what Monte Carlo is and created a lot of different visualizations to really help you try to understand this seemingly complex topic in a very digestible format. So Monte Carlo, as I said, is most commonly used for options pricing. And essentially what it does is that you simulate multiple possible paths and therefore future stock prices, and using each of those stock prices you can calculate the options price. So instead of simulating all possible stock prices, which would be impossible, you simulate a random sample of stock prices, and using the law of large numbers, which says that as the number of observations increases, our total mean average converges to the true population average. Using the law of large numbers, we can get a fairly close approximation to the actual option price. So something else that I also mentioned is that we can also use Monte Carlo for backtesting strategies. So in that case, later on, something we can realize is that the general framework is literally the exact same, but instead of using a option payoff function, we're simply evaluating the payoff of our particular strategy at the end of each path, averaging it over multiple different paths, and then taking the discounted value of that at the very end. So let's get started. So a little bit of background that'll help us understand Monte Carlo, first of all, is that we are assuming that there will be an annual return of mu, which means that if each period has length delta, then the per period return is going to be mu delta. So one example we can have is, say that mu is the annual rate, and then we're setting t, which is equal to n delta, which is the number of periods, times the time per period to be 1, which is normalized to be 1 year. Then that means that delta is going to have a value of 1 over 255, where 255 is the number of trading days, right, in a year. So that just means over the course of 1 year, we have 252 trading days, which means that the length of each trading day is going to be 1 over 255. So combining all of that, that tells us that if the annual return has a expected value of mu, then the per period return has a expected value of mu delta. And similarly, since we know that the variance of return scales linearly with delta, standard deviation scales with square root of delta, and we're also introducing another variable called epsilon, which we're taking to be a normal distribution with mean 0 and standard deviation 1. And we will realize what this is for later on. So we will define the gross per period return as mu delta, which is the mean return per period, plus the standard deviation times this factor. This is the randomized component. So think of S of t plus delta over S of t as just being tomorrow's return divided by today's return. So let's say that the stock price is 120 tomorrow and the stock price is $100 today, then this ratio is simply going to be 120 divided by 100, which is 1.2, right? That's how much the stock has changed from today to tomorrow. So as we saw, the gross percentage return is a good way to model returns. But what's more common in quantitative finance is to use something called log returns. And I will cover log returns in more detail in a different video. But all you have to know is that, for now, is that the percentage returns and log returns have the same variance, which is sigma squared times delta per period, but they have a slightly different expected return, where the simple percentage return has a expected value of mu delta, and the expected log return has a value of mu delta minus 1/2 sigma squared delta, where the second term is a small correction that comes from the fact that the log function is concave, right? So this means that the log return's expected value is always going to be less than the percentage return's expected value. And this is something that we're going to use because in Monte Carlo, we are modeling the effective log returns and then determining the stock price at the very end. That way we can perform additions as opposed to multiplications, which is the primary benefit of a log function. Okay, so those are the backgrounds. And I think a very good framework that we can sort of begin with to visualize options prices, and in particular in the context of Monte Carlo, is to think of it in terms of a binomial tree. So I created this visualizer that you can see here, right? So let's imagine that at each discrete moment in time, the stock price can either go up or it can go down. So let's say that if it goes up, it gets multiplied by 1.1, and if it goes down, it gets multiplied by 0.9. Now, what this means is that if we start at a stock price of $100, we're going to end up with a stock price of $110 or $90, where we have assigned the corresponding probabilities as, in this case, 0.76 and 0.24, right? So there's a 76% probability that we'll end up at $110 and a 24% probability that we'll end up at $90, okay? And then once we're at each of these states, we can once again have two potential possible futures, and so on and so forth until we reach the maturity, which would be the end of it. And at that point, we will know the stock price. Using the stock price, we can compute the option price. Averaging over all possible paths for the future, we can get the true option price via no arbitrage. But Monte Carlo simply says that as opposed to simulating all possible ending results, which we can see scales with 2 to the power of n, which would get extremely large, we simply simulate a random sample of them using Monte Carlo, and then using the law of large numbers, we can see that that will be very close to the actual stock price, right? So this is what the binomial tree is, and as we can see, which I will cover in a different video, we will see that the probability here, the risk neutral probability, actually ends up being 0.5. So as the limit as time approaches 0, p approaches 0.5 for both up and down. And it turns out that the binomial tree model is a relatively good way to model this scenario, okay? So that's our basis. So very simple, right? Like I said, at each point, the stock can either go up or down, right? Which means that, let's say that over n periods, we have u up moves and, or rather we have j up moves and n minus j down moves, then this would be our ending stock price. And then how many, ways can we get u up moves, right? That would just be computed by this, which you will know from learning statistics. And the total probability of getting exactly j up moves is this, right? It's n choose j times the probability of getting an up move times the number of up moves times the probability of a down move times the number of down moves. So that is simply the probability that we will end up at one particular ending node. Adding all of these ending nodes up and determining the corresponding call price at each ending node, we can get the options price. So that is how binomial works, and by simply understanding how the binomial model works, we also understand how the Monte Carlo works, because the Monte Carlo approximation is simply, instead of simulating all possible paths, we just simulate a random sample of it, right? So as we can see, we draw a uniform random number between 0 and 1, right? And then if this number is below p, which is our probability of an up move, we go up. If it's above p, we go down, right? We repeat this n times, we get a possible ending stock price. Plug it into the call price payoff function, we get the call price in that possible future. Simulate this n times. Using the law of large numbers, we can estimate the ending call price, right? So here's a visualization of what this looks like as the number of paths gets very large. So here we're simulating 300 possible paths, and as you can see, each line here traces out a possible future for the stock price. And then, using that future, we can simulate and determine a very close approximation for the call price. And that is why we use Monte Carlo for options pricing. Okay, so as we saw, law of large numbers, m approaches infinity, our mean gets fairly close with the variance getting reduced by a factor of 1 over square root of m. So the larger the m, the smaller the standard error. Okay, so before we were sort of thinking about Monte Carlo in terms of a very limited context, right? We're thinking of it in terms of the binomial model and also as if it were path independent, right? And then later on, we'll see what path independent means. Now, what if we thought about this in terms of log returns? Okay, so what does that mean, right? And then we'll skip over some of this because this is for the path dependent derivatives, but later on we'll realize that it's very similar comparing the path dependent and path independent. As we saw before, the log return has a mean of r minus 1/2 square root, or rather r minus 1/2 sigma squared. That's the mean return times delta, that's the mean per period return, and also the per period standard deviation is simply square root of delta times sigma, right? And then epsilon, which we assume to have a normal distribution here, is giving us this random factor. So at each point, the log return is going to have a mean of this and a variance, or rather a standard deviation of this, multiplied by a random draw, which we can simulate using our computer, right? That's what the log return is going to be for each period, right? And we can see that since log of a ratio is simply equal to log of the numerator minus the log of the denominator, moving the denominator to the other side and simulating this across each period for one possible path, we can see that, really this equation is very good because it helps us visualize what the Monte Carlo simulation even is, right? For each path, we have n independent periods. And for each period, all we have to do is take a random draw for epsilon. And since we know the sigma and we know the risk-free rate, we can determine how much to increment this by, right? So that's what we increment by per period. Now add that across all n periods, and finally add it to log of S naught, the initial stock price. This is going to be a number here because we know everything. We know R, we know sigma, and then we know delta, which we can find by just determining T, which is 1 divided by N, 252, right? We know this. Sum it over all of the paths. We know this entire thing on the right. Now raise both sides to the, raise e to the power of this, raise e to the power of this right side. We get what? We get ST. And ST is simply the terminal stock price at the end of the year. So now we have simulated one possible path, right? Now, we just do this exact same process m different times, simulating m different possible stock prices. And for each of them, we determine the option price. And once we determine the option price for each path and we average them, we just discount it back to today. And what do we have from there? We have the option price, right? So that's what all of this essentially says. And all of what Monte Carlo simulation is that it's a way for us to have a better sense of what the price of the option is going to be in the future, right? So a natural question that you have, you might have at this point is, why can't we just use the Black-Scholes, right? Black-Scholes is far more computationally, it's far less computationally intensive. It's just a closed form formula that you can just take your knowns, right? The stock price, the initial call price, and, the time to expiration, number of trading periods, just plug it in, right? And then you have the call price. And you are right that the Black-Scholes would be a very good approximation in the vast majority of cases. But realize that the Black-Scholes, two of the most important assumptions for the Black-Scholes model is, the first one is what? Is that this return, this risk-free rate of return is constant throughout the entire period. So if we have a period of an entire year, this R is not allowed to vary, right? Say it's 3%. Then we're using 3% for the entire year, and that's not very realistic. The second one is that sigma, or the volatility, is constant. So sigma also can't depend on time. So Black-Scholes is a very rigid model, and then later on we'll realize that if we assume constant risk-free rate of return and constant volatility, then we in fact get the exact same result for the Monte Carlo as Black-Scholes. If we repeat, the limit as m approaches infinity, the result for the Monte Carlo is going to be exactly the same as the Black-Scholes. So Black-Scholes is just Monte Carlo, but with a constant R and constant sigma, which is not very realistic. And the benefit of Black-Scholes, or rather the benefit of Monte Carlo, is therefore that we are allowed to vary sigma and risk-free rate of return throughout our simulation, which can be more realistic. And, finally, another thing that we can vary is this epsilon, which is the distribution. And here we're saying that it's normally distributed with a mean of 0 and a standard deviation of 1. But in reality, this can be any distribution because according to the law of large numbers, if we take enough samples, the mean is going to get very close to the population mean. Okay, so that's what the Monte Carlo approach does, and as I mentioned, so what's the difference between Black-Scholes and Monte Carlo? Why can't we just use Black-Scholes? Well, Black-Scholes assumes constant volatility, constant risk-free rate of return, no jumps in the stock price, which this can also be not necessarily a realistic assumption because stock prices do jump, say after an earnings event, right? Stock price is going to go from a very small value to a significantly larger value, and this assumption no longer holds. And also log normal rate of returns, right? I'm going to explain what this is in a separate video, but these are all the assumptions that Monte Carlo can relax, meaning that when we're using Monte Carlo for options pricing, we don't have to assume all of this. But again, right, our Monte Carlo approach is only as good, and we'll see this later on, as our model for sigma. How do we model sigma, right? And it turns out that one of the ways that we can model sigma is through a autoregressive stochastic process for volatility. Now, what does that mean? So that just means that we assume that volatility is mean reverting. And this turns out to be a very valid assumption because if you think about volatility, right, usually it stays at a certain level and it only varies dramatically from that level during things that are unexpected, like a earnings report or something else. So the autoregressive stochastic volatility, or the AR1 model, is simply a way for us to estimate this particular input in our Monte Carlo. And then I'm going to cover this AR1 process in a separate video where we will go through, 3 different approaches to estimating sigma, compare them and contrast them. And at the very end, in the part 2 of the video, we're going to analyze some limitations of Monte Carlo. So that is it for now. And if you enjoyed this video, please stay subscribed because I will publish many more content in the future on quantitative finance, options pricing, physics. So if you're interested in any of those, please stay tuned. And also I have linked the PDF for this video below. So thank you for watching and bye now.